The morning of December 7th, 1941, erupted into chaos at Pearl Harbor. American 5-inch anti-aircraft guns roared to life, their crews desperately tracking incoming Japanese aircraft through iron sights and mechanical predictors. For 90 minutes, the guns thundered without mercy. Over 1,400 shells screamed skyward, each one costing $50. The thunder rolled across the harbor, the smell of cordite thick in the air, smoke billowing from the gun mounts. Yet when the smoke cleared and the accounting began, the brutal truth emerged. Not a single confirmed hit. 0 kills against waves of attacking enemy planes. $70,000 had vanished into empty sky in just an hour and a half, enough money to purchase 2 comfortable homes in Honolulu. The failure wasn't one of courage or marksmanship. American gunners had done everything they were trained to do. The real culprit was something far more fundamental: the physics of the weapons themselves. Traditional anti-aircraft shells flew blind, entirely dependent on the gunner's ability to predict where a target traveling at 300 miles per hour would be 4 seconds into the future. Miss that calculation by just 0.3 of a second, faster than a human blink, and your shell detonated harmlessly in open air while the enemy aircraft continued its deadly dive. The British understood this mathematics intimately. During the London Blitz, they had fired 20,000 shells to bring down 74 German bombers. That worked out to roughly 1 hit for every 270 rounds fired. The odds were virtually impossible for any defender. In a basement laboratory in Baltimore, however, a South Dakota farm boy turned nuclear physicist named Merle Tuve was asking a question that seemed to border on madness. What if artillery shells could think? What if America built tiny radio transmitters into every shell, turning them into electronic hunters that could track enemy aircraft like bloodhounds pursuing a scent? The Pentagon dismissed it as physics fantasy. Yet within months, American factories would begin mass-producing shells that nearly never missed. The morning after Pearl Harbor, as smoke continued rising from the twisted steel of Battleship Row and casualty reports flooded into Washington, a different kind of assessment was taking place in the basement laboratories of Johns Hopkins Applied Physics Laboratory. Dr. Merle Tuve, a man of 41 years with the steady, practiced hands of someone who'd spent childhood summers repairing farm equipment across the South Dakota plains, was spreading preliminary combat reports across his cluttered desk. His stomach twisted as he absorbed the numbers. 1,400 rounds of 5-inch anti-aircraft ammunition had been fired at the attacking Japanese aircraft. The result: 0 confirmed kills. The mathematics were stark and devastating. American gunners had achieved a hit rate of 0% while expending enough ammunition to fund an entire small town's yearly budget. But Tuve grasped something the admirals and generals studying those same reports did not. This wasn't a failure of training or resolve, it was pure physics failure. Traditional anti-aircraft shells relied on mechanical time fuses, clockwork mechanisms that gun crews set by hand before firing. Each fuse would detonate the shell at a predetermined moment. The process was brutally simple and brutally unreliable. A gunner would estimate the range to an incoming aircraft, calculate how long the shell would take to reach that altitude, crank a small dial on the fuse to match that timing, and fire. If every calculation was perfect, if the aircraft maintained exactly the same speed and direction, if atmospheric conditions matched their assumptions, the shell might explode close enough to shower the target with shrapnel. In reality, something far harsher always occurred. A Zero fighter diving at 350 miles per hour covered 2,100 feet in the 4.2 seconds it took a shell to climb to 15,000 feet. Miscalculate that timing by 0.3 of a second, less time than a heartbeat, and $50 worth of carefully engineered ammunition simply vanished into empty air. The enemy aircraft sailed through untouched. The London Blitz statistics confirmed what Pearl Harbor had just demonstrated. Conventional anti-aircraft fire achieved hit rates below 1%, even under ideal conditions. Tuve had been wrestling with the anti-aircraft fire control problem since early 1941, when Dr. Vannevar Bush's Office of Scientific Research and Development tasked Johns Hopkins with strengthening American defensive capabilities. Most research teams focused on better mechanical predictors, faster calculation methods, more accurate gun mounts. Tuve had been pursuing something radically different, something his colleagues quietly thought impossible. What if the shell could make its own targeting decisions? The concept had sprung from a memory buried deep in his childhood. He'd spent summer evenings setting mousetraps in his family's barn. You couldn't predict exactly where a mouse would run, but you could position traps along every possible route and let the trap spring when the mouse drew close enough. Could an artillery shell work the same way? Could it wait until an enemy aircraft approached within lethal range before detonating automatically? The technical obstacles seemed insurmountable. A proximity fuse would require cramming a complete radar transmitter, receiver, antenna, and firing circuit into the nose cone of a 5-inch shell. The electronics would have to endure launch forces of 20,000 times Earth's gravity, enough to pulverize any conventional vacuum tube into powder. The system would operate reliably at altitudes reaching 30,000 feet and temperatures plummeting to -40 degrees Fahrenheit. It would need to distinguish between enemy aircraft and friendly forces. All of this within a package costing less than $50. In 1941, the smallest military radar installation consumed an entire room and required trained technicians standing nearby to operate it. The notion of shrinking such complexity into something smaller than a coffee struck most engineers as pure science fiction. Pentagon artillery officers were skeptical to the point of dismissiveness. Vacuum tubes were delicate laboratory instruments. Artillery shells destroyed things through brute force. The two concepts seemed fundamentally at odds. Then Pearl Harbor changed everything. Reports arriving from the Pacific painted an increasingly grim picture. Japanese aircraft attacked with seeming impunity, while American anti-aircraft fire proved largely ineffective. Similar messages arrived from Britain, where Royal Navy ships had expended 13,000 shells to bring down just 12 German aircraft during the Battle of Crete. The mathematical reality was impossible to deny. Traditional defensive fire was crumbling against modern air attack. Dr. Vannevar Bush, the MIT engineer commanding America's entire wartime research effort, summoned Tuve to Washington 3 weeks after Pearl Harbor. Bush's office overlooked the Potomac River, where construction crews labored around the clock to complete the massive Pentagon building that would house the War Department's burgeoning staff. Bush wasted no time with pleasantries. "The Navy wants better fire control computers," he said. "The Army wants improved gun mounts. I want something that actually works." Bush slid a folder across his desk. $2 million, 6 months. Make me shells that can think for themselves, or I'll find someone who can. Tuve returned to Baltimore carrying the weight of America's defensive crisis. Every day his team spent in research meant more American sailors and soldiers would face enemy aircraft armed with weapons that missed 99 times out of 100. The Proximity Fuse project, previously just an interesting technical challenge, had become a matter of national survival. Enemy planes weren't waiting for American innovation to bridge the gap with modern warfare. The race had begun, and failure would be measured in American lives lost to aircraft that conventional ammunition could never bring down. By March 1942, Tuve's team had transformed the Johns Hopkins basement laboratory into something between a radio repair shop and a munitions factory. Workbenches lined the walls, covered with oscilloscopes, signal generators, and dozens of prototype vacuum tubes smaller than a man's thumb. The air hung thick with the smell of hot solder and electrical ozone as engineers worked 18-hour shifts, driven by reports of American ships under constant air attack in the Pacific. The technical mountain before them seemed to grow higher with each design meeting. They needed to squeeze the functionality of a room-sized radar installation into 5 inches of diameter and 8 inches of height. The electronics had to survive launch accelerations of 20,000 Gs, forces that would crush a standard vacuum tube into metallic dust instantly. The system needed to generate its own electrical power, detect aircraft at precisely 70 feet, and cost less than a conventional mechanical fuse during mass production. Dr. Ralph Baldwin, Tuve's lead electronics engineer, had spent weeks calculating power requirements on a slide rule that never left his desk. "We need 4/10 of a watt for transmission," he reported during a particularly frustrating design session in early spring. "Another 2/10 for the receiver circuits, Standard batteries can't survive the launch forces, and we can't make the fuse large enough to hold batteries powerful enough anyway. The power problem seemed insurmountable until Baldwin remembered the spring-driven phonographs from his childhood. If a mechanical spring could spin a turntable through an entire symphony, perhaps it could power an electrical generator for the 25 seconds an artillery shell remained in flight. The answer emerged from this memory: a tiny generator powered by a spring-wound rotor that would spin during flight, creating just enough electricity to operate the radar for the shell's entire trajectory. The antenna presented its own complex challenge. Any external radio antenna would be torn away instantly by the tremendous forces of firing. Tuve's solution was elegant in its simplicity. The antenna was the shell itself. 4 metal strips built into the nose cone would create a radio beam pattern extending 70 feet in all directions around the shell's path. The projectile announced itself to the world as it hurtled downrange, but there was another obstacle standing in the way: those vacuum tubes inside the fuse itself. When fired through standard military radio tubes, they'd collapse and shatter once acceleration hit 500 Gs. But artillery shells experienced forces that dwarfed that number by 50 times over. Over in Harrison, New Jersey, RCA's tube division tackled the problem under blankets of secrecy. They needed to build sub-miniature tubes that could endure the crushing violence of a proximity fuse. The finished tubes measured barely 4/10 of an inch across. Inside, special filaments were reinforced, and shock-absorbing mounts were engineered to keep everything working even under 25,000 Gs of punishment. The real turning point came from an unexpected direction. A young physicist named James Van Allen, the same man who'd eventually mapped the radiation belts surrounding Earth, suggested a different approach. Rather than trying to make the tubes indestructible, why not make them resilient enough to survive damage? Fill them with particular gas mixtures, he proposed, and use thicker filament wire. The logic was compelling. If we can't prevent damage, we can engineer components that keep functioning despite it. By the middle of 1942, the engineering team had completed their first working version. The whole assembly tipped the scales at just over 2 pounds, yet it packed more electronic sophistication than the average household radio of that era. Nestled inside a container barely larger than a soup can sat 5 miniature vacuum tubes, a spring-driven generator, precise timing circuits, and a radar transmitter capable of spotting aircraft 70 feet away. It could withstand being launched from a cannon barrel. Trials commenced at Dahlgren Naval Proving Ground in Virginia, bringing mixed results. When test shells were aimed at radio-controlled target drones, the proximity fuses detonated successfully within lethal range about 85% of the time. They were functioning as intended, recognizing targets and firing at exactly the right instant. Yet something troubling surfaced during testing. The fuses sometimes triggered when passing near the firing vessel's own superstructure, responding to radio bouncing off steel hulls and radar antennas. The specter of friendly fire threatened to kill the entire project before it began. Navy gunnery officers understood the stakes perfectly. Weapons that might explode next to their own ships meant American sailors could die from their own ammunition. Weeks of tedious work followed as technicians adjusted the sensitivity, reshaping radar beam patterns to tell the difference between an aircraft and a warship's metal frame. Engineers developed what they called discrimination circuits, electronic intelligence that could separate the radar signature of an aircraft wing from the reflection bouncing off a ship's structure. These circuits didn't just measure signal strength, they studied patterns and how things moved. An airplane created a different radar picture than a stationary ship, which meant the fuse could recognize a genuine threat while dismissing friendly vessels. Even as testing moved forward, planning for production accelerated. Ordnance Bureau planners calculated they'd need millions of these fuses if combat proved their worth. American manufacturing plants would have to mass-produce electronics more complex than most store-bought radios, using methods that had never been attempted at that industrial scale. Workers assembling these devices would need to handle components requiring precision work beyond anything most had encountered, far more intricate than household electronics. A year after Pearl Harbor, December 1942 arrived, and production proximity fuses started rolling out of American Midwest factories. Many workers on these assembly lines were women, newly arrived in industrial jobs because wartime had created labor shortages. With steady hands and careful attention, they pieced together microscopic electronics. Everyone understood that every fuse leaving the factory would soon be aboard ships and heading toward enemy planes. American sailors and soldiers depended on weapons that actually worked. These fuses represented something bigger than better ammunition. They showed American industrial strength being weaponized against impossible problems. Across laboratories and factory floors from coast to coast, civilian researchers and manufacturing workers had engineered a weapon capable of independent thought, transforming defensive fire from a gamble into something approaching certainty when aircraft came within range. The first boxes arrived at Pearl Harbor in January 1943, packed in wooden crates labeled with cryptic numbers only. Admiral Chester Nimitz demanded total secrecy. No paperwork was to exist that might betray its capabilities if Japanese intelligence captured the information. Fleet gunners heard their instructions only through spoken words. Deploy the new rounds only above open water. Recover any shells that failed to detonate immediately. Report everything through encrypted communications alone. The USS Helena, a light cruiser that had absorbed terrible damage during the Pearl Harbor strike yet survived, became the first warship to fire these proximity-fused shells in actual combat. Her commanding officer, Captain Gilbert Hoover, had taken over after the original captain died in the Pearl Harbor assault. He stood on deck, watching binoculars as Japanese bombers approached near Guadalcanal on January 5th. The enemy came as darkness fell, their silhouettes black against an orange sky as they began bombing runs. Helena's 5-inch guns erupted at 12,000 yards distance, sending orange muzzle flashes into the gathering dusk. Instead of the black smoke clouds that marked the burst patterns of mechanical time fuses, the proximity fuses blazed brilliant white, appearing to chase the Japanese aircraft like glowing predators. The first bomber simply ceased to exist when 3 shells detonated within 70 feet of it, a tremendous burst of flame. A second attacker flipped onto its back and plummeted toward the ocean after shrapnel from a proximity-fused round tore through its wing. During those 15 minutes of fighting, Helena's gunners fired 32 rounds of proximity-fused ammunition and brought down 6 confirmed aircraft. The gunnery officer, Lieutenant Commander Robert Hagan, documented the action with barely concealed wonder. Historical data showed mechanical fuses required around 2,500 rounds per aircraft destroyed during the Guadalcanal fighting. This new ammunition achieved 18.75% accuracy, 50 times better than anything previous. Admiral William Halsey, commanding the South Pacific Force, nevertheless imposed strict limitations on the revolutionary ammunition. Proximity fuses could function only above water, never over land, where captured unexploded shells might let enemy engineers learn America's secrets. Navy divers had to retrieve every dud to prevent Japanese reverse engineering. Ships transporting these coded weapons received orders to destroy their stocks rather than risk capture. Word of the VT fuses, as they were cryptically designated, spread through the Pacific Fleet as more vessels received supplies. USS San Juan, operating near Bougainville in February, reported 4 confirmed aircraft destroyed using just 18 rounds. USS Oakland produced matching outcomes during darkness attacks near the Russell Islands. Her gun crews could strike targets barely visible through the night because proximity fuses eliminated the need for difficult range calculations. Commander R. Burke, heading Destroyer Squadron 23, watched the defense capabilities transform and analyzed what was happening with an officer's precision. Conventional anti-aircraft fire functioned mainly as psychology, Burke wrote in confidential reports to Admiral Nimitz. We generated noise and smoke that discouraged pilots yet seldom destroyed aircraft. These new rounds actually bring planes down. How our own personnel respond matters as much as the tactical advantage. Through intercepted radio messages decoded by American listeners at Pearl Harbor, Japanese pilots communicated their mounting fears. These American shells detonate without striking anything, explained one captured aircrew document from early 1943. Flying below 18,000 feet creates extreme danger. Japanese flyers adapted their strategy, shifting toward higher altitude approaches that sacrificed bombing accuracy for better survival odds. The numbers showed the transformation plainly. Fleet records revealed that ships equipped with proximity fuses consumed 85% fewer shells, achieving equal aircraft kills compared to conventional ammunition. Instead of needing 2,500 rounds per kill, they now needed fewer than 150. Ship survival rates during aerial attacks climbed by 40% since attackers were destroyed before launching weapons or finishing their bombing runs. Commander Joseph Crenshaw, commanding Helena's gunnery operations during later Solomon Islands engagements, maintained careful records of every proximity fuse action. His documentation showed consistent patterns. Aircraft falling at greater distances meant reduced damage reaching American vessels and enormously lifted morale among gun crews who finally witnessed their fire producing results. Personnel fight with different determination when weapons demonstrate real effectiveness, Crenshaw recorded in his logs. Greater aggression appears, confidence increases, men willingly engage targets previously considered hopeless. The weapon's remarkable effectiveness generated its own security headaches. Japanese intelligence analysts studying American anti-aircraft patterns correctly suspected some form of proximity detection capability. Radio intercepts revealed Japanese theories about radio-governed ammunition and magnetic fuses, though they never identified the actual radar-based mechanism. Admiral Ernest King, serving as Chief of Naval Operations, authorized counterintelligence campaigns designed to mislead. Disinformation circulated about improved optical devices and enhanced mechanical fuses. By mid-1943, proximity fuses equipped virtually every major American warship operating across the Pacific. American manufacturing plants were producing over 200,000 fuses monthly, each containing electronic parts surpassing most civilian radios in complexity. The manufacturing accomplishment rivaled the tactical achievement. American industry had mastered mass-producing sophisticated electronic weapons using assembly processes originally developed for automobiles and household products. The human consequences of this technological success appeared in Japanese casualty statistics that American codebreakers intercepted. Elite bomber crews representing the finest Japanese naval aviation were being eliminated faster than replacement programs could produce them. The technological edge was reshaping the fundamental equations governing air-sea combat, making standard aircraft virtually incapable of successfully striking well-protected American vessels. What started as a scrambling effort to enhance American defensive strength had transformed into a game-changing weapon, fundamentally shifting the Pacific War's power balance. 2 months following the D-Day operations in June 1944, General Omar Bradley confronted a challenge threatening to strangle Allied supply efforts throughout Western Europe. German V-1 flying bombs, launched from French and Dutch positions, kept striking the vital port of Antwerp with terrifying precision. These pilotless weapons flew at 350 miles per hour between 1,000 and 3,000 feet altitude, too low for heavy bomber interception, too rapid for conventional anti-aircraft responses to track effectively. Bradley recalled witnessing proximity fuses revolutionize naval defense in the Pacific. Admiral King's security protocols, however, prevented their use across land, where adversaries could gather unexploded ordnance and decode America's most carefully protected technical secrets. The potential danger of German technicians unlocking this capability overshadowed any immediate tactical benefit. Yet with beachheads secured in Normandy and German forces retreating eastward across France, Bradley argued the restrictions should finally be lifted. Antwerp's harbour represented the lifeline of the entire Allied advance across Europe. More supplies flowed through this single Belgian port than any other facility on the continent. If German flying bombs succeeded in destroying it, the entire momentum toward Germany would grind to a halt. Months of delay, thousands of casualties, possibly even a stalled offensive. The stakes couldn't have been higher. The decision to take action came from the very top of the Allied command structure. General Dwight Eisenhower, after extensive talks with the combined chiefs of staff, made the call. American forces would begin using proximity fuses for air defense around critical installations. Yes, there were security risks. Yes, Germany still had research facilities working on countermeasures. But with more and more German labs falling under Allied control, the benefits clearly outweighed the dangers. On August the 15th, the first shipments of VT fuses arrived at land-based anti-aircraft batteries defending Antwerp harbour. The orders were unmistakable: protect the port at any cost. Colonel James Morris commanded the anti-aircraft defence around the harbour. He'd positioned his 90mm guns with surgical precision around the dock facilities, each battery sighted to create overlapping fields of fire. His crews had trained hard with conventional mechanical time fuses, and they'd achieved respectable results. About 1 in 5 V1s destroyed during earlier engagements. Flying bombs were actually easier targets than manned aircraft in some ways. They flew in straight lines, maintained steady speeds, never dodged or evaded, but their small size and low altitude still made them devilishly hard to hit with traditional methods. Then came August 22nd, the moment that would prove everything. The Germans launched a concentrated assault, 47 flying bombs streaking toward the harbour in a concentrated wave. Morris's guns roared to life at maximum range, and the new shells, the ones with proximity fuses, filled the grey morning sky with brilliant flashes of detonation. What happened next stunned everyone watching. 39 V1s exploded before reaching their targets, an 83% intercept rate. That was impossible. It contradicted everything they'd experienced with conventional ammunition. At Battery C, Technical Sergeant Robert Hayes sat glued to his SCR 584 radar scope, watching the engagement unfold on his screen with pure fascination. Those shells seemed to have minds of their own. Every single time a V1 appeared on his radar blip, the proximity shells would detonate almost on command, right at the target. "We were shooting down things we could barely see," Hayes reported later, using equipment that seemed to think faster than any of us could move. The impact rippled far beyond that single engagement. German supply operations through other channels kept getting disrupted, but Antwerp's docks kept moving cargo. The V1 attacks became an exercise in futility. Allied codebreakers intercepted German intelligence reports showing desperation setting in. German commanders were reading their own failure in real time. The enemy defensive fire has achieved near-total interception capability. Red 1 decoded message from German 15th Army headquarters. V1 operations against Antwerp are no longer cost-effective. Stop attacks on this target. Luftwaffe tactical manuals were being rewritten across German commands. Captured documents from late 1944 contained stark warnings to pilots: never approach Allied-controlled territory below 20,000 feet. German pilots were submitting reports describing the accuracy of American and British anti-aircraft fire as suicidal at low altitude. The proximity fuse had changed everything. It transformed air-ground combat the same way it had transformed naval warfare. The industrial achievement behind this success was staggering. American factories were churning out over 400,000 proximity fuses monthly by autumn 1944. Each one cost just $18, actually cheaper than conventional mechanical fuses when you factored in the improved kill rate. Every single fuse contained 5 vacuum tubes, precision timing circuits, a spring-powered generator, and radio components more sophisticated than most home radios of the era. All of it manufactured to withstand being fired from a cannon. The human dimension became clear when you looked at the casualty figures. Ports, airfields, and supply depots that used to suffer constant damage from German air attacks now operated with barely a scratch. Allied bomber crews reported dramatically fewer losses to German anti-aircraft fire, especially as Luftwaffe fighter strength dwindled due to fuel shortages and pilot losses. The technological advantage was spreading through every corner of the air war. Captain William Patterson commanded Battery A of the 320th Anti-Aircraft Artillery Battalion. He watched the transformation ripple through his gun crews. The men fought with genuine confidence now. Patterson recorded in his diary, "They know their shells will connect with what they're aiming at." Instead of hoping for lucky shots, they're calculating firing solutions and engaging targets that would have been absolutely impossible with mechanical fuses. The proximity fuse had changed more than just hit percentages. It had changed the soldiers themselves, transformed how they thought about their work. German efforts to develop countermeasures ran into walls. Luftwaffe technical intelligence correctly figured out that American shells were using some kind of radio proximity detection. But when they tried jamming techniques or electronic deception, nothing worked. The engineers at Johns Hopkins had built in sophisticated discrimination circuits that German radio jammers simply couldn't defeat. Those German radar jammers designed to confuse Allied aircraft navigation systems proved useless against proximity fuses, which operated on completely different frequencies using entirely different signal processing. By winter 1944, proximity fuses had become standard ammunition for every major Allied anti-aircraft battery in Europe. The technology that had started as a desperate fix for Pearl Harbor's defenses had evolved into a complete answer for the air defense problem that had haunted military commanders since aircraft first appeared in combat during World War I. The era of effective defensive fire had finally arrived. The ultimate proof came in the waters west of Guam. June 19th and 20th, 1944. Naval historians would call it the Battle of the Philippine Sea. Admiral Raymond Spruance's Task Force 58 centered on 15 aircraft carriers. Facing them came Japanese Admiral Jusaburo Ozawa, commanding 9 carriers and launching 430 aircraft in a desperate gamble. Ozawa believed concentrated attacks by skilled pilots could still break through American defenses. But Ozawa didn't know what awaited him. Task Force 58 was the most heavily defended naval formation ever assembled. Every major ship carried proximity-fused ammunition. The entire fleet's anti-aircraft batteries worked together under SCR-584 radar systems, tracking hundreds of targets simultaneously. Admiral Mark Mitchell had arranged his ships in circular formations designed to create overlapping fields of fire that would engage incoming aircraft at maximum range. The first Japanese strike appeared at 0830 hours on June 19th. 169 aircraft flying in tight formations toward the American carriers. Task Force 58 opened fire at ranges exceeding 20,000 yards. Proximity-fused shells filled the sky, detonating in brilliant white flashes throughout the attacking formations. Lieutenant Commander David McCampbell was flying combat air patrol in an F-6F Hellcat when he watched the spectacle unfold. The sky looked like the 4th of July, he reported afterward. Every shell seemed to find a target. Japanese planes were exploding everywhere. The numbers told the devastating story. The first Japanese wave lost 142 aircraft before reaching their targets, an 84% casualty rate. Coordinated attacks became impossible. Pilots separated from their formations by anti-aircraft fire attempted desperate solo runs against American carriers, but the defensive systems, now operating at near-perfect intercept capability, destroyed them systematically. One after another went down. The second Japanese strike brought 130 aircraft. 107 were destroyed by American defensive fire. The third wave suffered 95% casualties. Only 7 aircraft made it back to their carriers. By the end of the first day, Admiral Ozawa had lost more than 400 aircraft, his entire striking force gone. Minimal damage inflicted on American ships in return. Japanese pilot reports intercepted by American radio intelligence conveyed utter hopelessness. Enemy defensive fire is impossible to penetrate, one surviving squadron leader transmitted. Shells explode continuously around aircraft without direct hits. Recommend abandoning attack missions until new tactics are developed. But there were no new tactics. No pilot skill could overcome the physics of a proximity fuse. Any aircraft flying within 70 feet of an American shell was destroyed, period. Captain R. Burke stood on the bridge of his destroyer, watching the engagement unfold. He understood exactly what he was witnessing. "This isn't just a naval victory," he wrote in his personal log. "This is the end of carrier aviation as an offensive weapon. No aircraft formation can survive defensive fire this effective." American pilots called it the Great Marianas Turkey Shoot. But it was more than a tactical victory. It marked the end of Japanese naval aviation as anything resembling an effective fighting force. The industrial achievement backing this military triumph was equally remarkable. American factories produced over 22 million proximity fuses by war's end. Each contained electronic components more advanced than most commercial radios available to civilians. The miniaturization techniques developed for artillery shells had pushed American electronics manufacturing decades ahead of where it had been before the war. Workers in plants across the Midwest, many of them women entering industrial work for the first time, were mass-producing precision electronic devices using methods that would later power the post-war electronics revolution. Dr. Morel Tueve directed proximity fuse production from his laboratories at Johns Hopkins. The South Dakota farm boy who had approached this impossible problem by breaking it into pieces had created a weapon that fundamentally altered warfare. "We didn't set out to revolutionize military technology," Tueve reflected in a post-war interview. "We just wanted American sailors to come home alive." But sometimes the most important innovations come from asking questions that everyone else thinks are impossible to answer. The proximity fuse's legacy extended far beyond the battlefield. The vacuum tube miniaturization techniques developed for artillery shells became the foundation for post-war electronics advancement. The precision manufacturing methods needed to mass-produce complex electronic devices enabled the consumer electronics industry that would transform American society in the 1950s and 60s. The tiny radar transmitters built to survive being fired from cannons led directly to transistor development, integrated circuits, and eventually the microprocessors that powered the digital revolution. By war's end, proximity fuses had achieved a 61-fold improvement in anti-aircraft effectiveness while using 85% fewer rounds per destroyed target. The technology saved an estimated 100,000 American lives by improving ship survival and reducing aircraft losses. More importantly, it demonstrated that American industrial innovation, properly directed and adequately funded, could solve seemingly impossible technical problems and tip the balance of warfare through superior engineering rather than superior numbers. The small device that had begun as a desperate attempt to improve Pearl Harbor's defenses had become the weapon that ended the age of aircraft terror. It proved that sometimes the most powerful innovations come not from building bigger guns, but from teaching existing weapons how to think for themselves.